Okay, in chapter 4, we just discussed how to solve higher-order linear differential equations by using superposition principle, how to solve homogeneous differential equations, how to solve non-homogeneous differential equations. We talk about especially two different approaches to find a particular solution to the non-homogeneous differential equation. Today we're going to start a different approach to solve differential equations. In general, it can be solved using this method for first order differential equation, but they can be also used in higher order differential equations. So this is a brand new method that applies to all differential equations, and that's called the Laplace Transform. By using Laplace Transform, we will be able to convert a differential equation into a normal algebraic equation. We can convert the first order linear differential equation, for example, into a linear equation. We can convert the second order differential equation into a quadratic equation and so on. And then we can solve those equations easily. After that, we're going to use the so-called inverse Laplace transform to convert the solution into the original domain. And then we obtain the solution of the original differential equations. So in sample 1, let's just introduce this Laplace transform. So what's the definition? All right, it is an integral transform first. So that means you just integrate something from the original equation and get another function. So so let f be a function defined for t greater than or equal to 0. So that's the function f, and the variable is t, not x. All right, it has to be non-negative. So then we define the integral e to the negative s t times ft. Integrate from 0 to infinity. All right. So you can see you are integrating over the variable t. So after integration, it becomes a function of s. Remember, in this exponential e to the negative st, we have s as a parameter or a new variable, and t is a dummy variable. Okay, so at the end, you get a function of s. And we call this result, this integral, improper integral, by the way. We denote it by script L of f of t. I mean, to mean it's a Laplace transform of the function f. Okay, so this whole thing is said to be the Laplace transform of f, provided that the integral converges. So what does it mean by convergence? It means the integral makes sense. Remember in Calc 2 when you learned improper integrals, we have an infinity in the upper limit integration. So that's defined based on the limit. You just integrate the function from 0 to some parameter b, and then you let it be approaches infinity. So that takes a limit with b approaches infinity. If that limit exists, then we call this integral converges. Okay, just remind you the definition of convergence of integrals. So that's the definition. All right. So it's an integral transform. You just multiply the function by factor e to the negative s t and integrate t from 0 to infinity. So let's just do some simple examples from the definition. So we want to evaluate error of 1. So the function is constant function. Ft equals 1. We want to find the Laplace transform of this function. So according to the definition, it's the integral from 0 to infinity of the function e to the negative st times ft, where ft is 1 in here. So at the end, it just integrated from e to the negative st from 0 to infinity. And from the definition of the improper integral, as I just mentioned, you integrate e to the negative st from 0 to b and take the limit with b approaches infinity. Okay, so we can easily integrate e to negative st. You treat s as a parameter and t as the variable, and you're going to get e to the negative st, but at the same time you need to divide negative s when you integrate, and this can be easily done by integrating by substitution. If you let u equals negative st, okay, that's what you get. And then you just evaluate t at b and 0 and subtract. All right, so I'm not going to repeat the whole process of integration by substitution. We did the in Cal 2. All right, so the whole thing is just the limit from -1 over negative s times e to the negative s b minus e to the negative s times 0 with the b approaching infinity. Okay, if you plug in t for b and 0 in the result in antiderivative, actually it's called antiderivative, and then negative s times 0 just 0, so we got the second term e to the 0, which is 1. So at the end it just becomes 1 with negative s e to negative s b minus 1 with b approaches infinity. But if you still remember, the function of exponential function e to the negative sb, where b approaches infinity, and we know s is some parameter or constant positive. Okay, so we require this s to be positive in order for this integral to converge. So in other words, e to the negative sb will approach 0 when s greater than 0. So s is positive when the b approaches infinity, so you get the very large number in the exponent, but it's negative. So then the exponential of that with base e is just a 0. The limit is 0. When s is less than 0 or equal to 0, you can see s cannot be equal to 0, by the way, because you get 1 over negative s in the denominator. When s is less than 0, it's negative, so you get the negative s positive, and then times b, because b approaches infinity, so the positive, so you get a positive, a huge number in the exponent, and it is positive, and that just blows up. You don't get a limit in that case. So this Laplace transform converges only when s greater than or equal to 0. When it converges, the first term e to the negative sb with b approaches infinity, it's just 0. The limit is 0. So you just left with -1 times 1 over negative s, and it's just equal to 1 over s. So that's the Laplace transform of the constant function 1. You just get the 1 over s. But the whole thing has to be, valid, which requires the parameter s to be positive. Okay. So that's the first example, and then let's do another example how do we find the Laplace transform of L of t? So this function f is t. Okay, ft equals t, basically. So just replace ft by t again in this integral. So we just integrate e to the negative st times t from 0 to infinity from the definition. Okay, so again, you're going to do the improper integral. By the way, what do you mean by improper? Here it because the upper limit of integration is infinity. Okay, so you still need to integrate from 0 to b and take the limit with b approaches infinity. Okay, so how do you integrate this t times e to the negative st respect to t? I just give you a hint using integrating by parts. You learned integrating by parts in Cal 2, so you have to use the integral parts. Okay, you got to define some u and v, dv, those things. So in here, you just let u equal to t and e to the negative st dt equal to dv. Okay, and then use the formula of integration by parts. What you're going to get is just t times e to the negative st over negative s minus e to the negative st over s squared. Okay, after you are done with integrating by parts and finish the whole process. That's what you get for the antiderivative. And then you need to evaluate this antiderivative at t equal to 0 and b and subtract. Okay, so once again, we're going to require s to be positive in order for the integral to converge because of the exponential of e to the negative st. We want to make the we want to make sure the exponent e negative st to be positive, to be negative. For that to happen, because b is positive, so s has to be positive also. So the whole thing negative st is negative and large in magnitude. And when you take the limit, this exponential is just 0. Okay, so we don't have to worry about the limit of the whole thing as b approaches infinity because it will be 0. So what do you do? Just plug in 0 for t, but you have to put a negative sign in front, and we use again e to the 0 is 1. When you multiply s with 0, you get 8. You get 0. Okay, so so the first term actually also vanishes because when you plug in 0 for t, you get 0 times something, so that term vanishes. So the whole thing is just the second term with t equal to 0 plugged in and putting another negative in the front. Okay, so you got two negatives, so it becomes positive, and the e to the 0 is just 1. So the whole thing is just 1 over s squared. Okay, so the Laplace transform of function t is just 1 over s squared, and again we have to make sure s is positive. All right, any questions about this example? The next example is the Laplace transform of e to the t plus 7. So again, just plug in ft equals e to t plus 7 in the integral. So the integral is just e to the negative st times e to t plus 7 integrate with respect to t from 0 to infinity. So you can do a little simplification before you do the integral. You can just factor out t to 7 out of the whole thing because it's constant. Remember, you can break up e to the t plus 7 as e to the t times e to the 7. And when you add the exponents, it means you multiply two exponentials. And then you can factor out t from the remaining exponentials, combine them. You get e to negative st plus t for the integrand, and after you factor out t from the exponent, it becomes e to the negative s plus 1 times t. Okay, and then you integrate this thing from 0 to infinity, and using the definition of improper integral again, you integrate from 0 to b and take the limit with b approaches infinity. Okay, integrating over t. So this is easy to do because we just use the substitution in integration by substitution again. If you let u equals negative s plus 1 times t and do the integration by substitution, you're going to get the e to negative s plus 1 times t and then divide by negative s plus 1. Okay, I'm not going to repeat that. You can do it, but check it by yourself easily at home. Okay, so then what they do is just plug in 0 and b and take the limit. So once again, when you plug in 0 for t, then you get a 0 times the negative s plus 1, so that's 0. E to 0 is 1 again. So that one is straightforward. And then you plug in t for b. Okay, so you get e to negative s plus 1 times b. And again, because b approaches infinity, is positive. In order for this integral to be convergent, or this limit to exist, we have to require a negative s plus 1 also to be negative. Okay, so because b is positive, so we have to make sure the exponent is negative and large, so that when you take the limit, it becomes 0. So negative s plus 1 has to be negative. So that means negative s plus 1 less than 0. So if you solve this inequality, you move s to the right. The solution is actually s greater than 1. So in this case, the parameter s has to be greater than 1 for this Laplace transform to converge. Okay, so in that case, when you take the limit with b approaches infinity, the exponential has the limit of 0. So we got the 0 in the first term, and we just minus 1 over negative s plus 1 again, because e to 0 is 1 when you plug in 0. So if you just distribute this negative sign denominator, it becomes s minus 1. So the whole thing is just the e to 7 times 1 over s minus 1, or e to 7 over s minus 1, with the requirement of s greater than 1. Okay, so that's the Laplace transform of e to t plus 7. All right. Any questions?